this invasive Russian
Okay.
students aren't getting the full picture.
Oh, let me pause that. All right. Good morning, lads and ladies. Welcome back to College Algebra. I hope everybody had a nice, safe, pleasant spring break. Today, we are going to pick up right where we left off. So we left off, you may recall, talking about one-to-one functions. We learned some operations on functions, specifically that composition operator, the f of g thing. And then we discussed what it means for a function to be one-to-one. And I promised you that there was going to be a very special operation that was related to a function being one-to-one. Today, we are going to introduce that thing. I have a few little announcements for you. So let's get the QCANs. Let's get the title card up and we can go through the announcements and then begin on the material. Oh. Here we go. Ooh, that is. Sometimes my cats come in here and just do whatever the hell they want with this setup anyway. See if we can bring the contrast back down to something reasonable. That is definitely not reasonable. There we go. Oh. Okay. So this is MAC 1105 section 015, which is college algebra. And the date today is the day after Pi Day. 3/15. So I mentioned a few announcements. One of these has to do with quiz 13, I think it is, the quiz that I opened up for you just before break. Let me actually show you. So homework 13 was set to be due today. Where is this? Oh no, set to be due yesterday. So what I was doing here is I intended these to be due on Tuesday, not on Monday. And so because I think some of these dates were off by one, yeah, I'm going ahead and pushing these to Thursday. Now, of course, the intent was for you guys to work those over the break. This was the material that we talked about the Thursday before spring break. But because these were both accidentally set to come due on Monday rather than today, I'm pushing them to Thursday just in case anybody had intended to work them like yesterday and didn't get the chance to finish them up. So homework and quiz 13. So those will be due on the 17th now, this Thursday. The other one is regarding your exam. So the partial credit for exam 2. I have not been able to enter this yet. It was a very busy break for me, but I'll be working on it through this week now that we're back home. So this will be added over the next week. So just keep an eye on your Canvas assignments and your Canvas announcements and stuff like that. If there's an issue with something that you submitted, then I may need you to give me some information, some feedback. Conversely, you probably want to get the feedback that I'm going to give you. So I'll be marking up your work and putting partial credit into my open math over the next week. Okay, so today we're going to talk about inverse functions. And I think it would be wise, because we did just have a week-long break, to recap a little bit some of the stuff from the operations of functions. So let me begin here by saying something like recall. A function f is called one-to-one if kind of in words, the simplest way to say this, let's see here, what is this? Oh yes, Kylie, thank you for that reminder. Yeah, there's a nice warm-up exercise we're going to do here. So let me first put down this definition, and then we can go back and look at those as warm-up exercises. So a function f is called one-to-one if different inputs go to different outputs. That's sort of the simplest way to say it. If it sends different inputs to different outputs. Now, if you combine this with the definition of a function, you get kind of two different restrictions on the input-output pairs. Remember, in order for a relation to be a function, it can't send any one input to two different outputs. And that was the vertical line test that we had at the beginning of the semester, right? If a vertical line touches the graph more than once, then that graph is not a function. A one-to-one function says that every output has to come from one and only one input. And if you combine these two things, you can get a simple statement. So a relation is a one-to-one function means that f of x, the output from the input x, will be equal to f of y, the output from the input y, if and only if x is the same as y. And this is sort of your simplest way of saying it, right? So no input can go to two different outputs. That means you're dealing with a function. And then no output can be hit by two different inputs. That means your function is one-to-one. And together, that means this, right? In other words, a one-to-one function is something that pairs unique individuals of the domain with unique individuals of the range. It is we call it a one-to-one mapping. In other words, it means that for every one guy in the domain, there's one and only one guy in the range, and vice versa. Okay. We also had those operations on functions, f plus g, f minus g, f times g, f over g, and f of g. Turns out the f of g operation is going to interact very nicely with this one-to-one thing. There were a few questions from that previous homework set that I was asked to look at our first day back in class here. So let me go ahead and do that, and that can kind of serve as our warm-up exercises. So we want to look at homework 13, questions 21 and 22. And we're specifically curious about, what was in 21, C and D. Yeah, and that's good. That's about what we're looking for here. And then in 22, we wanted part B. Okay, so let me transcribe this. So this is our little review on operations of functions. F of x is the square root of 2x plus 4, and g of x squared minus x, h of x is 1/4 x. And I'll just go ahead and do parts C and D here. So to find f circ h of 8. And part D, we want to find g of x plus b. So getting nice and comfy with the function notation and the symbols that represent the new operations, composite or composition operator, the circle here, both very important for what we're going to be talking about today. To find f of h of 8, remember the only real thing to do here is to apply the definition. So if you're ever stuck or lost on one of these problems, trust in this first step of just writing down the definition. F, little circle, H of 8. This is F of H of 8. Is the same thing as F of H of 8, written like this. Right, this F circle H is just the name for the function where you plug into H and then take that output and plug it into F. Remember the machine diagrams? Once you have this, we work from the inside out. So what is H of 8? Well, H of X is right here. So if I plug 8 in for X, I see that H of 8 is going to be 1/4 times 8. The F on the outside is still there. Inside I have 1/4 times 8. Well, 1/4 times 8 is 2. So this is F of 2. And then I look to the function F over here. F says, whatever you feed me, I'm going to multiply by 2, then add 4, then take the square root. So this is the square root of 2 times 2 plus 4. Now 2 times 2 is 4. 4 plus 4 is 8. So this is the square root of 8. And that's the first part. Questions on this one? All right, let's take a look at the second one, because this guy is also important, especially if you intend to go on to calculus. Dealing with expressions like this is a very, very big deal. So we want G of X plus B. Remember Friday before last, we talked about finding like F of dog shit, F of your mom, F of whatever. You just plug in for X, whatever the expression is in the parentheses here, right? So remember, when you write something like this down, it's a rule that tells you how to find the output for any given input. So if you plug dog shit in here, you get dog shit squared minus dog shit. G of your mom would be your mom squared minus your mom. So G of X plus B is X plus B squared minus X plus B. And we always do this when we're plugging into something, we always do it in parentheses. How much you want to work with this is up to you. You could FOIL this out if you want. You could just leave it like this. I would be perfectly happy with this. But just for fun, let's see what happens if we FOIL this out. There might be some cancellation. So this would be X squared plus 2bx plus b squared. And then when I distribute this negative, I'll get minus x minus b. And there's really not a whole lot we can do. This 2bx has an x. This guy also has an x. But it's not especially pretty. If you wanted to, you could write this as x squared plus 2b minus 1x plus b squared minus b. If you wanted to put all the x's together. The 2b minus 1 coming from 2bx minus 1x. So you kind of put those next to each other and then factor the x out to get 2b minus 1.
On the test, would we have to break it down like that?
I would be perfectly happy with this. Yeah. So no, you would not have to get to this. I would be perfectly happy with this. The other one we wanted to take a peek at here was okay, so my open math has sometimes been giving us a little bit of a hard time. Let's take a look at the instructions here. They might say that they want the answer rounded to a decimal or something. 2√2. So you can simplify this. We'll keep it in purple. So the square root of 8, remember that 8 is 4 times 2. And then you can give the square root to each piece. Remember when we were dealing with quadratics and we had to break up square roots like this? And then the square root of 4 is 2. So this really is 2 root 2. The key isn't incorrect there, but it doesn't tell you that you have to simplify. So I'm not sure why. I think maybe I'll make a little note here. So it's 21C. Sorry, another. Okay. Yeah, I'll take a look and see if we can fix the key. So if you entered that as the square root of 8, you should certainly get credit for it because that is absolutely correct. Just happens to also be the same thing as 2 root 2. I can see how that would be frustrating. Any other questions or comments on this one? We also wanted to take a look at number 22, part B. Is there anything else good in here? 22. Let's look at both B and C. So here we're told that f of x is 2x plus 1. And g of x is x squared minus 2x. And we're told to find g of x plus h, and also f of g of x and then compose the other way, g of f of -1. So the two little pieces in part C, this could be a bit misleading, are actually very different. In the first part of part C here, you're finding f of g of x. And down here, they're asking you for g of f of -1. So the composite is being done in the other order, right? Rather than being fog, this one down here would be like goff. So you won't be able to get the second piece of part C from the first piece. You'll have to do a separate computation. Let's go ahead and see how it looks. So g of x plus h, this is the same sort of thing as like finding f of your mom or f of dog shit. We're going to look at the expression for g of x, and everywhere there's an x, we're going to write parentheses x plus h instead. So that will give us x plus h all squared minus 2 times parentheses x plus h. All right, like this. So again, this function notation, you can think of these parentheses as like a mouth, or whatever metaphor you want. Just make sure that when you're asked for some function of some stuff, what you're doing is you're plugging that stuff into the original expression for x and doing so everywhere in parentheses. So right here, this becomes x plus h. That's this. Right here, this becomes x plus h. That's this. It's very different than adding h on the outside. You could, again, leave this like this if you wanted, or you can flow this out, and you get x squared plus 2xh, that's your inners and outers, plus h squared, and then distributing the -2, you get minus 2x minus 2h. In both pre-calc and calc 1, dealing with expressions like this will be a very important thing. There are like terms we could combine here. I've got 2xh minus 2x. It's up to you if you want to do that. I'm a little short on space. I'll just leave it like this, but I would be perfectly happy with this. This is a correct answer. In the next part, we want f of g of x. And again, the only thing to do here is to start with the definition. By definition, this is f of g of x. And then we work from the inside out. G of x is x squared minus 2x. So this is f of x squared minus 2x. And then we look to f. F says, whatever you feed me, I multiply by 2, and then I add 1. So f of dog shit would be 2 dog shit plus 1. F of your mom would be 2 times your mom plus 1. F of x squared minus 2x is 2 times x squared minus 2x plus 1. And we can leave it like that. That's fine. If you want to distribute, you can. You get 2x squared minus 4x, and then this 2 is not going to the 1, right? The parentheses end here, so just plus 1. You get this little quadratic. And I think part C is intended to trip you up a little bit. I think it's pretty natural to think, oh, well, now I want this, so I'm just going to plug -1 in here. But this is not the same as this. Right? This is f of g. This is g of f. So we really do have to do a separate computation here. They've already kind of done the first step for us, right? This thing kind of looks like this thing. So now we're going to work from the inside out. I need to figure out what f of -1 is and then take g of that. So my g on the outside is going to stay. F of -1 is 2 times -1 plus 1. And because the inside here is just a number, no variables, it's nice to simplify this before trying to plug it into g. So I'll leave the g on the outside here. I'm just going to figure out what this number is. 2 times -1 is -2. -2 plus 1 is -1. So this is just g of -1. And now I'm just looking for g of some number. Well, here's the formula for g of x. We just plug that number in for x. So it's going to be -1 squared minus 2 times -1. -1 squared is +1. And 2 times -1 is -2. Minus -2 is +2. So this is going to be 3. Okay. A little quick and dirty review of operations with functions, emphasis on the composition operator. I'm going to backtrack now a little bit to help us visualize one-to-one functions so that we can understand this special new thing called an inverse. You may have noticed that anytime I talk about fractions like 1/5, I never call it the inverse of 5, and there's a good reason for that. I always call it the reciprocal, because in mathematics this word inverse is reserved for something a little bit different, and that something is inverse functions. When you think about what a function does, let's look at a mapping diagram for a 1-to-1 function f. And the domain is over here. The range is over here. And I've got some stuff here. Maybe I'll call it A, B, C. And I've got some stuff over here. Maybe I'll call it X, Y, Z. And we understand that maybe F maps A over here to X. Maybe F maps B down here to Z. I could send C to Y. I could send C to X. I could send C to Z. Any of those would be okay, and F would still be a function. But if I want F to be a 1-to-1 function, the input C has to go to the output Y. If I sent C to, say, Z, then it would not be true that different inputs go to different outputs. I would have 2 different inputs, B and C, being sent to the same output, Z. So if I want this to be a 1-to-1 function, F has to do this. In other words, a one-to-one function is a perfect pairing, right? It pairs up individual elements of the domain with individual elements of the range, in the sense that for every one guy over here, there is one guy over here, and for every one guy over here, there is a unique guy over here. So a one-to-one function f pairs elements from the domain with unique elements of the range. The reason one-to-one functions are so nice is because the concept of an inverse for functions is just turning the arrows around, having the arrows point back the other way. If I want such a thing to be a function, then I need the original to be one-to-one. So let me add in these arrows. I send x back home to A. I send y back down here to C. And I send z back up here to B. The blue arrows represent the inverse function. Let's say the inverse to such a function is a new function that sends all of the outputs from F back to the inputs from which they came. This is the big idea of an inverse. It's the function that undoes whatever the function f did. So f sends a to x, f inverse will send x back to a. F sent b to z, f inverse will send z back home to b. F sent c to y, f inverse will send y back home to c. The fact that f is one-to-one is very important if you want the inverse to be a function. So quick little note here. If f is not one-to-one, then f inverse will not be a function. Let me try to illustrate this to you. So again, let's imagine some function f has inputs a, b, and c. And over here in the output space, I just have two things, x and y. Suppose f sends a to x, sends b to y, and also sends c to y. The inverse here just turns the arrows around. So sends x back to A, but it has to send y to both B and C. So the outputs for F are the inputs for F inverse. The black arrows here do represent a function. The blue arrows here do not. Why do the blue arrows here not represent a function?
Because y is going to both B and C.
Perfect. F inverse is not a function. Because its input y is sent to two different outputs. Namely B and C. So the outputs for the original, F, are the inputs for the inverse, F inverse. So Y is an input for the blue function, for the blue mapping. For F inverse, this is an input, and this input is being forked and sent to two different outputs, which means that the blue arrows do not represent a function, right? Because remember, a function has to send every input to just one output. This behavior here, where you've got two inputs for the original function going to one output for the original function, is called a 2-to-1 mapping. You see where the name comes from? There's two guys that get sent to this one guy over here. So that's the black not being 1-to-1. And that failure of being 1-to-1 of the original function is exactly what produces the failure for the blue mapping to be a function itself. So we want the inverse of a function to be a function. And that's why 1-to-1 functions matter, right? If a function is 1-to-1, then it has an inverse, which is itself a function. That's the big idea. Let me go ahead and define for you in terms of the composition operator. Now let's see how this connects to what we were doing before, right? 1-to-1 functions have inverses, which are themselves functions. We have special operations for functions. And the standard definition of an inverse is given in terms of that composition operator. Given a 1-to-1 function, F, we can define the inverse of F, denoted F with a little -1 up here, and that's not a power, right? It just means the word inverse in the sense that we were just discussing, turns the arrows around, runs the machine backwards. Sure, yeah, we can look at a table. Denoted F inverse by the rule. And I'm going to write this down in two different forms, one using that like circle symbol and one just using the function notation with the parentheses. Okay. So imagine that F inverse is the mapping that turns the arrows around. If I do F inverse of F of X, so I take some input X, I apply F to it, then I apply F inverse to that, what should I get out? F is the black arrows, here's an input. F inverse is the blue arrows that turn the black arrows around. So we start with an input, do the black arrows to it, then do the blue arrows to that. Where should I end back up?
Would it be F, the inverse of F to X, and then f to x, f of x.
It's true that if we're going to write this out in the definition, it would be f inverse of f of x. But I want to jump a little further. So I start at some, here, let me come down here.
Oh wait, was that multiplying or of?
Of, yeah, composition.
Oh, okay.
So I start at some input, I apply f, and then I apply the inverse to that. I end up right where I started, right? Start at some input, apply the original function, then apply the inverse to that. I end up right back where I started. Start at some input, apply the original function, then apply the inverse. I end up right back where I started. So f inverse of f of x, it's just x. The two functions undo each other. You end up exactly where you started. And it also works if you compose in the other order. Don't get hung up on the symbol x here. Remember, x just represents an arbitrary element of the domain or range. So if I start at some x, I do the blue arrow to that. That brings me back over to this side. Then I do the black arrow to that. That brings me right back to where I started. This is the definition of an inverse function. Now, each of these can be written a different way. I will show you the other way, and then I'd be happy to look at an example through a table. If you write down kind of the definition of the circle operation here, this says that f inverse of f of x should just be x. And same thing down here. If you write down the circle thing as the parentheses thing, this would say f of f inverse of x, like that, should just be x. So these are the two notations for the definition of an inverse function. Intuitively, f inverse is the function which exactly undoes f. So in terms of like machine diagrams, if f takes a soda bottle, an empty soda bottle, and fills it up with soda, right? Empty bottles come in, full bottles go out. Then f inverse would take in full soda bottles, drain them, and spit out empty bottles. So if you do the two right in a row, you end up with whatever you started with. If f is the function put on your socks, then put on your shoes, then f inverse would be the function take off your shoes, then take off your socks. Because if you do one followed by the other, you start with a bare foot, you end up with a bare foot. If f is the function square root of x, so you take a number, take its square root, then f inverse would be the function x squared. Because if you take a number, take its square root, then square that, you get the original number back. F inverse is the function that exactly undoes whatever it is that the original function f does. And I do think a table is a good way to play with these. So we can take a look at an example for a table. Let f be described by the table. Find a table for f inverse. So here, let me give you a table of x's and f of x's. Maybe f sends 0 to 2, sends 1 to 3, sends 5 to 1, and sends 7 to 4. So we should first ask ourselves, does this table represent a one-to-one function? How would you answer that?
No, because they don't share inputs.
I think you're thinking on the right line. I'm just not sure I'm fully understanding what you're thinking. So what do you, I do believe this is a one-to-one function. But what do you mean by they don't share inputs? Let's flesh out the thought. I think it's a good thought. I'd like to hear it.
Like the x's don't have the same y's that correspond with them.
So like, you mean this would have to be a 0, this would have to be a 1, this would have to be
Yeah, that's what, yeah. No, I'm talking about like, so it would be like 0, 2, and then it would be 1, 2. And then it would be,
so yeah, you're on the right track there. That would mean that the function is not one-to-one.
yeah, that, yeah.
Yeah, so if both 0 and 1 were sent to 2, then this function would fail to be one-to-one, right? Because the two different inputs, 0 and 1, would be getting sent to the same output 2. So if we want to know if this function is one-to-one, we should ask ourselves, are there any two distinct inputs that get sent to the same output? So do different inputs get sent to different outputs? If the answer to that is yes, then this function is one-to-one. In other words, what you want to look for are repeated outputs, right? Like when you're checking if something is a function, you look for repeated inputs. If you're checking to see if a function is one-to-one, you look for repeated outputs. Are there any repeated outputs here?
No.
Good, yeah, so this is a one-to-one function. No repeated inputs, so it's a function. No repeated outputs, so the function is one-to-one. So then how would we find a table for the inverse? Remember, the inverse should send every output from the original function back to the input from which it came. So what will be my list of inputs for the inverse function?
The top would be 2, 3, 1, 4, and then the bottom would be 0, 1, 5, 7.
Perfect, perfect. The inputs for the inverse are the outputs for the original. So 2, 3, 1, and 4. F, the original function, sent 0 to 2. So if F inverse is going to undo that, F inverse needs to send 2 back to 0. The original function F sent 1 to 3. So for the inverse function to undo that, it must send 3 back to 1. The original function sent 5 to 1, so the inverse has to send 1 back to 5. The original function sent 7 to 4, so the inverse has to send 4 back home to 7. This would be the table for F inverse. And you can check that for any particular number x, these relations are satisfied. Sometimes being left-handed is just the worst because I want to write over here, but then I'm going to cover this. Let's check that F inverse of F of x is equal to x. Because we have a finite domain here and we don't have a formula for either function, we just have to check one at a time. So when x is equal to 0, F inverse of F of 0, well, what's F of 0? F of 0 is 2. So this would be F inverse of 2. And then we look at the table for F inverse. F inverse of 2 is 0. So is F inverse of F of 0 equal to 0? Yeah, right. So this statement is verified for that particular input 0. We can check for x equals 1. F inverse of f of 1. This should, at the end of the day, be equal to 1. Let's see. Working from the inside out, this is f inverse of, well, what's f of 1? F of 1 is 3. So this is f inverse of 3. Looking at the table for f inverse of 3 is 1. So this is good. This is good. We can check when x is equal to 5. We should get f inverse of f of 5 is equal to 5. Well, f of 5 is 1. So f inverse of that is f inverse of 1. F inverse of 1 is 5. Okay, it works. And we can check for 7. Why not? We're already here. F inverse of f of 7. This should, at the end of the day, simplify to 7. Well, the inside here, f of 7, according to the first table, is 4. So this is f inverse of 4. And then looking at the purple table, f inverse of 4 is 7. And you can kind of get a feel for what this might mean in terms of the graph. Remember, each one of these columns is an ordered pair on the graph of the original, right? This says that the 0.5, 1 is on the graph. This says that the 0.1, 5 is on the graph. So ordered pairs get swapped from the original to the inverse. So let's discuss this in terms of the graph really quick. And then I'm going to show you how to solve for an inverse algebraically. Here's a fact. You can call it a theorem. The following are equivalent. 1. The point A, B is on the graph of F, the original. This means that f of A is equal to B. I should say for a one-to-one function F. Right, that's what it means to say that A, B is on the graph. Go ahead. Oh, sorry. Oh, I think it's car keys. Here. Well, this means that F sends the input A to the output B. And that would mean that F inverse sends its input B to its output A, right? F inverse undoes whatever F does. But that means that F inverse of B is equal to A. And that means that the point B, A is on the graph of F inverse. All of these are equivalent statements. And it's going to tell us something deep about the graph of F and F inverse. Take item 1 and item 6. If the point A, B is on the graph of F, all this shit tells us that the point B, A is on the graph of F inverse. In other words, to get the graph of the inverse function from the graph of the original function, you flip over the points. You exchange the x's and the y's. You reflect over the line y equals x. A consequence? Just say it. Graphs f and f inverse are symmetric about the line y equals x. That's one. Another, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. The x's and y's get swapped, which means the set of all x's, the domain for the original function, becomes the set of all y's, the range for the inverse. And the set of all y's, or outputs for the original function, becomes the set of all inputs, or x's, domain for the inverse. We said this already, but I want to make sure you have it in your notes because it's something that will save you on a handful of problems. I'll give you a minute to write, and then we're going to do an example. And then I'll show you how to find the algebra expression for the inverse of a function. Questions on this? Okay. So here's a classic. I give you the graph of f, and I ask you to sketch the graph of f inverse. Function f is graphed below. Sketch the graph of f inverse. And this particular function I'm going to graph for you is not one that you're able to write down a formula for just yet. Let's go 1, 2, 3, 4, 6, 7, 8, something like that. And let's keep it simple. How about 0, 1, 1, 2, 2, 4, 3, 8. And over here, let's say this point is -1, 1/2. And we'll do something like this. Let's give ourselves a little asymptote on this side. Let's say we do something. Oh, here's the original function f. Let's see if we can sketch the inverse. I'll label these other points too. So this is 1, 2. This is 2, 4. This it's 3, 8. All right, so we got plenty of points to play with. Here I'll give myself lots of space to graph the inverse. And off to the side, I want to use that theorem to see if we can find some points on the graph of the inverse. So I'll just list those points that are on the graph of f. I've got -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. How do I find points on the graph of the inverse function?
You could just flip it.
Yeah, we flip the coordinates of each point over. So if -1, 1/2 is on the original, then 1/2, -1 is on the inverse. If 0, 1 is on the original, then 1, 0 is on the inverse. If 1, 2 is on the original, right? It's not hard. 2, 1 is on the inverse. 2, 4 on the original means 4, 2 is on the inverse. And 3, 8 on the original means 8, 3 is on the inverse. So for my x's here, I'll need to go out to 8. Let's go 1, 2, 3, 4, 5, 6, 7, 8. My y values, I've got a -1 here, and 1, 2, and 3. So 1/2, -1. That would be like right here. 1, 0. That's right here. 2, 1. That's right here. Let's see, 1, 2, 3, 4, 2. That's right here. And 8, 3 would be right about here. So we end up with a curve looking like this. And just how this spot goes over and over and over, and you have this horizontal asymptote, this piece will go down and down and down, and you'll have a vertical asymptote. So this would be the graph y equals f inverse of x. And I want you to note that there's a special symmetry here. If I were to pick this graph up and set it on top of this one, they would be symmetric about the line y equals x. I'll show you what I mean in Desmos, because it's a little bit hard to transpose these because I've used different scales. I should label these points too, right? This was 1, -1, this guy was 2, 1, this guy was 4, 2, and this guy was 8, 3. I mentioned that these are functions that you guys don't know how to write down formulas for yet, although we will learn how to write down formulas for them eventually. This is called an exponential function, and the new unit we're working on is going to be all about exponential functions and their inverses, which are called logarithm functions. So don't worry about the symbols I'm going to type in here. Just pay attention to the graphs. Here's the original black function here. And here's the inverse. Okay. Can you see the symmetry? And add in the y equals x. See, if I take this black function and I flip it over this green line, I get the purple function. If I take the purple function and I flip that graph over the green line, I get the black function. When I said the graphs of f and f inverse are always symmetric about the line y equals x, that's what I mean. And it's precisely the same thing as saying you flip over the points, right? Being symmetric about the line y equals x means when you exchange y and x, things stay the same. So here I have a point on the original, on the inverse, and if I reflect that across this line, that means I'm switching the x's and the y's. That will give me a point on the output. Like, let's look at 3, 8. Here's a point on the original. And 8, 3. Here's a point on the inverse. And you see that the way you get one point from the other is just by reflecting over this line. And if you do that with the whole graph of the one, you get the whole graph of the other. Cool stuff, right? Okay. So the big question at this point should be, how do I find the inverse of a function? First, you need to know that a function is 1-to-1 in order to find its inverse. We have a test to see if a function is 1-to-1. The easiest test is coming from the graph. So let's take a quick look at number 6 here. We'll lab it, because I don't want to have to graph this by hand. That would be a lot of work. So if I want to sketch this graph, I can turn on my calculator. If you have your calculator with you, please go ahead, grab it out. I can wait for just a second. I'm going to hit this y equals button, and then I'm going to type in this expression, x cubed. I'm going to get down out of the power by hitting the arrow over, and then plus 2. And I'll hit graph. So I want to know, is this function 1-to-1? I should be asking, does it pass the horizontal line test? Who remembers what the horizontal line test says? Anybody remember that from the Friday before break? That's
It's not 1-to-1 if the line hits the graph more than once.
very good. Yeah, if there is any horizontal line, hits the graph of f more than once, then f is not 1-to-1. So I want to know, is f of x equals x cubed plus 2 1-to-1? I want to know this because my goal is to find the inverse if there is one. So we pulled out our graphing calculator and we got a nice picture of the graph here. You can sketch it really quick. It's nice to have it on paper so you can play with it. Looks like our y-intercept is up here at at 0, 2. And we've got this kind of S curvy shape. And you can come in here and draw a bunch of horizontal lines. Do any of these hit the graph more than once?
No.
Correct, yeah. So since no horizontal line hits the graph more than once, f is 1-to-1. You have a handful of problems like this in your homework. Sometimes they give you the graph. Sometimes they give you the function like this. If they just give you the formula for the function, plug it into your graphing calculator. Give yourself a little sketch of the graph and try drawing horizontal lines through it. If you can make any horizontal line hit that graph more than once, then the function is not 1-to-1. But if no horizontal line hits the graph more than once, then the function is 1-to-1. If you're working with a table, then you need to do like we did earlier and ask, are there any repeated outputs, right? Repeated outputs would indicate that a function is not 1-to-1. So the big question at this point is, given a 1-to-1 function, you know how to sketch the graph of its inverse, but how do you find a formula for the inverse? So, question. Given a formula for a 1-to-1 function f, how do we get a formula for its inverse, f inverse? I think because of the notation, because this -1 here kind of looks like a power, we're often tempted to just like take the reciprocal, but that's not it at all. The answer here is to solve for the output in terms of the input, or starting with the original function, you solve for the input in terms of the output. In other words, the steps here, you're going to write y for f of x, solve for x in terms of y, meaning get x alone. And then you're going to swap x and y. I know some high school teachers tell you to swap x and y first. That's bad policy. Don't do it like that because you get confused about questions of domain. Solve for x, then swap. And then finally, you just relabel this y as f inverse because that's swapping. Now you're swapping the domain and range. So you're now changing f into f inverse. So these are your steps. Let's see if we can execute this at least once. We can do it with the function we were just working with. We've already verified that x cubed plus 2 is a 1-to-1 function. So let's see if we can find the inverse of that 1-to-1 function. If your original function is not 1-to-1, then finding the inverse is pretty futile unless you restrict the domain. And we'll talk about that a little bit later, but for now, we're just going to work with 1-to-1 functions. So here's our procedure. We said we want to solve for this input in terms of the output. So I want to first write just one symbol for this output. It's a little bit jarring to have an f of x everywhere. So we're going to write y equals x cubed plus 2. That's my first step. Now the second step can get a little complicated because, you know, solving equations can be hard, but here it's not that hard. If I want to solve this for x, the first thing I would do is subtract the 2 over. I get y minus 2 equals x cubed. And then to get rid of that cube, to get rid of that third power, I can take the cube root on both sides. And since the cube root, that's an odd root, I don't have to worry about a plus or a minus over here, right? Odd roots don't do that, only even roots do that. So this is step 1. These 2 lines are step 2. Now we're going to swap x and y. So I'll write the cube root of x minus 2 equals y. And then we relabel y as f inverse. So the cube root of x minus 2, that is f inverse of x. So I'll number the steps here. This is 1, this is 2, this is 3, this is 4. So in other words, f inverse of x is the cube root of x minus 2. And I'd like to graph this function for you on top of the original function in our calculator to see that the symmetry really is there. Before I do that, any questions on the actual steps here? Okay, let's see it. So here's the graph of my original function. Let's leave that in there and also graph this guy. I'll type here a cube root of x minus 2. We can hit the right arrow to get out of our cube root, so we make sure we've got everything typed correctly, and now I hit graph. See the symmetry? If you add in that line y equals x, right here, you see that these graphs are perfectly folded over that line. Add in the line y equals x to see that they're perfectly folded over that line. There it is. There's your line of symmetry. Pretty cool, right? We have a few seconds left, so we can try one more. Something like this can be a little bit challenging. So let's do this. Quickly verify that you don't have any non-one-to-one functions here that are being asked for inverses. No, okay, good. Yeah, we do that in pre-comp, but we're not supposed to do that here. So we have this guy. I want to find f inverse of -5, and they've given me a formula for f of x. Change the numbers just a little bit. It's nice to be aware of what you're looking for. So when I say find f inverse of -3, what that means is I'm looking for the input for the original that gets sent to the output -3. But you can stare at this all day and not realize what input's going to get sent to -3. It's a tough question to answer directly. So what we should do is find the inverse function, f inverse of x, and then plug -3 into that. So first I'm going to find f inverse of x. Then I'm going to plug x equals -3. That's our strategy. To find f inverse, I need to run through that 4-step process. So I first write y equals x plus 2 over x plus 1. And I chose this particular example because finding the inverse for rational functions like these can be a little bit tricky. X shows up twice here, so it's not immediately obvious how you solve this for x. Let me show you. Your end goal here is to get all the terms with x on one side and all the terms without x on the other side. Then you can factor in x and divide over. That's the game. So to get all the terms with x on one side, first I need to get rid of this fraction. So I'll multiply both sides by x plus 1. When I multiply both sides by x plus 1, the x plus 1s go away over here. And over here, I just have x plus 1 times y. Then we distribute on the left. I'll have xy plus y equals x plus 2. Right? Just distributing here, y times x, y times 1. Again, the intermediate step is to get all the terms with x on one side and all the terms without x on the other side. So here's a term with x. Here's a term with x. I want those two terms on the same side. Here's a term without x. Here's a term without x. I want those two terms on the other side. So I'm going to subtract this y over here. I'm going to subtract this x over here. That gives me xy minus x equals 2 minus 1. Now on the left-hand side, because every term has an x, I can factor that x out. Get x times y minus 1 equals 2 minus y. And finally, I can divide over by the y minus 1 to get x alone. So all of this is step 2. Right, here's step 1. All of this is step 2. Now step 3, we swap x and y. Step 4, we write f inverse in place of y. So f inverse of x 2 minus x over x minus 1. Step 4. So now you have your inverse function. In our strategy, we said we're going to find that inverse function and then plug x equals -3 because we wanted f inverse of -3. So if I plug -3 in here, I get f inverse of -3 is 2 minus -3 divided by -3 minus 1. Upstairs, 2 minus -3. 2 plus 3 is 5. Downstairs, -3 minus 1 is -4. So this is -5/4. And that is your answer. Inverse functions, they're good stuff. They're very good stuff. And they're going to allow us to define certain functions in the future as inverses of other functions in cases where we don't have a means to define the function that we want to work with, namely logarithms. Right? Logarithms are a family of functions that we will define to be the inverses of exponentials. And that's all we're going to have to work with them. We won't have formulas or anything like that. So you need to get comfy with inverse functions. It's going to take some practice. Take your time on this homework. If you end up needing more time on it, that's fine. Reach out to me if you want help with it. That's fine. Reach out to me. Come by office hours, send me Canvas messages, emails, whatever you can, and I'll be happy to help you. But make sure you work hard here. I promise it will pay off in the next part of the course. The next part of the course is generally considered the hardest, right? Exponentials and logs, specifically logs. The better you understand inverse functions, the easier logs will be. So invest the time here. I promise you it will pay off before exam 3. If there's anything you want to talk to me about, I've got an office hour from 11 to 12. I'm available through Canvas, email. You all know the drill at this point. partial credit for your exam 2 will be going in over the next week. And that is it from me. So take care, guys, and I'll see you next time.